morning, good afternoon, good evening. Welcome those viewing asynchronously. It's terrific to have you as a participant. Um, kind of related to where we're headed and coming out of Matt's very kind introduction. As a quantitative methodologist, a lot of my work involves the development and application of quantitative methods as they play out in a variety of contexts. Primarily things like latent variable models that show up in educational, psychological, and behavioral science applications. Quite often, much of my work involves using Bayesian methods, which is what brings us here together. I've had the really good fortune to teach Bayesian methods in a number of different contexts, including an introductory Bayes method seminar for Statistical Horizons. Our seminar is pitched as a second course. We'll do some review of foundational models and topics, and then move into more advanced scenarios. I really like to thank Statistical Horizons for having me to teach this second seminar. And again, thanks folks for joining us. A little bit of administrative setup before we kind of dive in. I like to keep things fairly informal, so I like and welcome questions and comments and discussion along the way. I encourage that. Also on the administrative end, you should have received access to slides, software files, data sets, and exercises. If for some reason you don't have access to them, be in touch. We'll figure it out, get it to you. If you're stuck on installation in the software, it looks like there was a comment that came in earlier about that. Be in touch and we'll work with you to figure it out maybe during one of the breaks. One of the things you should have access to is a set of exercises for folks to work on their own time. At the end of each of our day's session, I'll point to these for folks to work on if they wish. Any administrative questions about our plans structurally for our time together before we dive into some material, or at least an overview of where we're headed? Then I'm going to start. If you look towards the first set of slides that you should have received, I'm going to start sharing that in a moment. We'll work off of those. So I'm just going to go over briefly kind of an overview of where we're going to spend our time. I like to kind of have a plan of our tentative schedule. Day one, I feel pretty good about. Day two and day three, I'm not sure where we're going to get to on each day because I never know how long things will take when I teach them. But this is roughly the sequence. Certainly what we're going to do today. We're going to start off in just a little bit on reviewing foundational material in Bayesian inference, building up through regression modeling. And that's really going to be our launch point to take a deeper dive into factor analysis. We're going to spend a good bit of our time today talking about factor analysis for a couple of reasons. One, some of the models that we're going to talk about afterwards can be thought of as building off of regression and factor analysis. And two, even if you don't look at it that way, a lot of the tools and things that we will develop in our treatment of factor analysis, we're going to put into play when we talk about those other things: structural equation modeling, multi-level modeling, missing data modeling. So a lot of those ideas and techniques and tools, we're going to spend some time on in factor analysis today, and then we're going to deploy them routinely later on. As I said, exactly when we'll finish day one material and start day two material, is that going to be at the end of the time today? Will some of it bleed over into our time tomorrow? I'm not sure. We'll see how it goes. Every time I teach things, it takes different amounts of time. But this is, broadly speaking, the plan for our time together. And before I give a kind of some more details about my orientation to things, let me say one more note about the topics here and what we can glean from them. My hope is that if you're factor analysis person or a structural equation modeling person or a multi-level modeling person or a missing data modeling person, you will get a lot out of those topics. In addition, even if you find yourself saying, well, I'm not really a multi-level modeling person, that's not much of what I do in my work, I'm not really sure if that's really suitable for me. My hope is for each of these modules to accomplish two things. One is to talk about the topic of the module, like, say, multi-level modeling, but also to talk about general Bayesian principles. That is, general principles of inference as they occur or play out across different applications of Bayes inference. So in talking about factor analysis, or in talking about structural equation modeling, or in talking about multi-level modeling, and so on, even if you're not someone who uses those procedures extensively, what we're going to try to weave in is general Bayesian principles that apply more broadly that you could take to whatever analyses or things you engage in. Any thoughts or questions about this kind of plan or overview? I see some questions or things coming in on the chat regarding software and so on. I'm going to hold off on addressing them. I'm happy for folks to communicate or share concerns or questions or answers. That'd be terrific. That's absolutely fine. But if folks are having trouble with installation or running of software, I'm going to hold off on that until we get to software later on. We have limited time together, so I like to try to emphasize where I'm going to put my focus. And what you can see here is where I'm going to put my emphasis on conceptualization. We'll do quite a bit of practice with things like real code on real data sets, implementing things and talking about different options for code in some point, but we don't have time to cover all different software and all the different options. You can see there's going to be a pretty low emphasis on things like mathematical theory. This is not a course intended to talk about theory of or the mathematical theory of Bayesian inference. We're much more, what are the ideas? What are the concepts and principles? And how do we use them in applied data analysis? Along the way, because I can't help myself, I will tend to sneak in a little bit of philosophy to the extent that I can, or at least how I see it. I'll add that I use a few different examples of different situations and contexts in this course. In describing or illustrating or using our techniques, I like to use real-world examples rather than just toy examples that are made up to work perfectly. I recognize that in using these kinds of examples, folks may have different resonance, personal, cultural, political, or otherwise, with these contexts or examples that you may find disconcerting. I certainly don't intend to produce discomfort or harm, but my choices of using of real-world examples, there are several reasons, one of which is I want to highlight that analyses can be brought to bear on difficult real-world problems, including those that might have those kinds of resonances for folks. Nevertheless, my door is open. I certainly invite folks, if you would like to discuss the use of any example or topic in our time together, please contact me. On the use or choice of software for our time together, there are competing notions here. there are different software applications we could use. They can have various trade-offs. Some software that is appealing because it's more flexible or more general, and it can handle lots of different things. On the other hand, other software might be more appealing because it's more targeted use for specific applications. Software differ in accessibility, or how expensive they are, or how easy they are to use or interface with other software, whether they are more coding or menu driven. And so there are a lot of different directions we could go when learning about Bayesian methods. There's a nice kind of set of possibilities that we could choose from. In our time together, this is the environment we're going to work in. Looking at the lower left, we're going to use the R statistical environment as kind of our home base for setting things up and data management for our time together. And we will use R packages to interface with STAN, a software for fitting Bayesian models. And we're going to do all of that under the umbrella of RStudio. RStudio is an interface for working with the R statistical environment. These are not the only choices you could make. These are the ones that these are some of the ones we're going to use in our time together. When we look at software, I will point out different folder structures for data sets and examples and so on, including other software. So even though we're not going through other software in our course, in some cases I've included examples. So you say, well, I'm more of an M+ user for things like factor analysis or structural equation modeling. Okay, there's some examples about how to do Bayesian analysis using M+ in our files, even though given our time constraints, that's not something we're going to cover in our time together. So any administrative questions that folks would like to raise or discuss about where we're headed in our time together, or the orientation of this course or this seminar before we turn to foundational Bayesian material? Well, then I'm going to hop over and let's see if we can call this up. The next set of slides should be titled something like this, Review of Bayesian Inference. And this is where we're going to spend our time now to kind of get us started. For some of us, this is a refresher of things we might have learned, maybe in the first course that was offered through Statistical Horizons on Bayesian inference. For others of us, this might have echoes of things we learned about in other coursework, or in some other exposure to Bayesian methods, like doing projects or doing analyses or reading about Bayesian methods. And still, for others of us, this might be a more deep presentation than anything we've yet seen in Bayesian inference, and that's okay too. What we're going to try to accomplish here is really hit the main themes of Bayesian inference as they play out in a few different situations, building up to regression models. So what is Bayesian inference? I like this quote from Don Rubin. Rubin writes, a Bayesian justifiable analysis, and you can just ignore that justifiable and just think, what's a Bayesian analysis? Is one that treats known values as observed values of random variables. That's usually stuff like data. Data are going to be modeled as random variables, that is, having distributions. Treats unknown values as unobserved random variables. That is, unknown things like model parameters are also treated as random variables having distributions, and then calculates the conditional distribution of the unknowns given the knowns and model specifications using Bayes' theorem. Some of the ingredients, if we look at Bayes' theorem here, if you look on the left side, we have one term, and on the right side, we have several different terms. I'm going to work through them on the right-hand side, and then we'll look at what that yields on the left-hand side. I'm also going to introduce the color coding that I will tend to use throughout. So what this slide is highlighting is the term in blue. In notation, that is the probability distribution for theta. Theta is a generic representation of an unknown parameter here. So the term in blue all the way on the right-hand side in the numerator is a distribution for the unknown parameter theta. In the context of Bayes inference, this is a prior distribution. Prior meaning it contains everything we know or believe about the parameter theta before we observe value for the data, which is going to be expressed as x. What I will try to continue to do throughout all of the slides is use blue font to refer to things that are associated with prior distributions. Sometimes I depart from that convention, but for the most part, blue is kind of a signal. We're talking about prior distribution stuff. The term next to it in red is the conditional probability of x, the data, given the parameter theta. Notice the way that I'm writing it. Px vertical bar or pipe theta indicates this is a distribution for x conditional on or given the parameter theta. Once the data x are observed, this term becomes our likelihood function, the likelihood function for the unknown parameter. Again, I'm going to try to color code things, and most of the stuff that has to do with the distribution of data given a parameter, I'm going to color code in red. Finishing out on the right-hand side, the term in the denominator is the marginal probability of the data, x, marginalizing over the parameter theta. If we have a discrete parameter space, it's a sum of basically all possible numerators. In a continuous space, as we'll see, it's an integral. This term is actually often not important for us. If you notice in the notation, the unknown parameter theta doesn't appear. It's just px. It's the probability distribution of x, of data. In practice, we often don't need to specify this. We can discard it from our model specification. In other words, we can work with just the important terms in the numerator, and that is enough to execute Bayes inference. This is thanks to the kinds of software we use these days. So those are the three terms on the right-hand side. The real action is in the numerator. The term in red is the distribution of data given parameters, and the term in blue is the prior distribution for those parameters. Putting them together yields on the left-hand side now the answer in a Bayesian analysis, the posterior probability distribution for the unknown parameter theta given the data x. Again, look at the notation. P and then theta vertical line x or pipe x here indicates we're looking at the distribution of theta conditional on after having observed the data x. This posterior distribution is our answer, loosely speaking, as a Bayesian. It captures what we think about the unknown parameter now that we have incorporated the observed data x. I've color-coded things related to the posterior in purple. I will try to continue to use purple to refer to things having to do with the posterior distribution. Here is Bayes' theorem written out for discrete variables. On the left-hand side, there's our answer, the posterior distribution. That's what we're often after. And then looking at what that's equal to on the right-hand side, let's see, we have the term in red is the conditional probability of the data x given the parameter theta. The term in blue is the prior for the theta. The term in the denominator is the marginal probability for the data. We could think about expanding that marginal probability in terms of the sum over all possible numerators. But as we just mentioned a moment ago, if we actually ditch the denominator and just work with the terms in the numerator, what we get is something that is proportional to the posterior distribution, and that's often good enough. If our parameter or variable space here is continuous for theta, instead of the marginalization being a sum, it's an integration. But the same logic applies. If I just ditch the denominator and talk to you about the numerator, that is enough to construct our model to obtain the posterior distribution. I like to think about this three-step approach to Bayesian modeling that comes from Andy Gelman and colleagues. Step one, set up the full probability model. What is the full probability model? The joint distribution of all the stuff. Stuff includes known stuff, x, like data, as well as unknown stuff, like theta, our parameters. Set up the joint distribution in accordance with all that is known or understood about the problem at hand. And that joint distribution there on the left side is a distribution of all the stuff, observed and unobserved. And our strategy as modern day Bayesians is to talk to you about it in the pieces we've already mentioned. What's the conditional probability for the data given the parameters, multiplied by the prior for the parameters? A real useful shortcut for those of us who are new to Bayesian methods, but have a lot of familiarity with other modeling techniques, is to do the following kinds of steps. Write out your model the way you're used to writing it out. If that's an equation, if that's a diagram, however you like to think about your model at hand. If you're used to writing out models or specifying statistical models a certain way, do that. Then go through that model and look for all the unknown parameters. What are the unknowns here? And those are the things that in the final stage here, we would specify prior distributions. This is not the only way to go about doing things, but this is a convenient way. Set things up the way you're used to doing with the conditional probability of data, whatever you're used to doing, and then go list out the parameters that need prior specifications. All of this, I would say, is step one, model setup. That's just expressing the model that you would like. Step two is to turn the crank of Bayes' theorem. Get the answer. That is, condition on the observed data to calculate the conditional probability distribution for the unknown stuff, theta, given the observed data. That is, get the posterior distribution. For some simple situations, we can do the math and do this analytically. We say this is our model, so this is our posterior distribution. For pretty much all the stuff we're going to be covering in our time together, we're not able to get the analytical solution. The model is too complicated. We cannot do the math by hand, so to speak. Instead, we will rely on software to arrive at the posterior distribution for us. So step one is model setup. Step two is, in some sense, fitting the model to get the posterior distribution. We will heavily rely on software to do that for us. And then the third step here in this three-step approach is whatever it is you're used to doing with statistical analyses and statistical output, you can do with Bayesian analyses. So if you want to examine the fit of your model, or compare competing models, or evaluate certain hypotheses, if you want to test the reasonableness of the assumptions, or scratch your head and think, do these conclusions make sense? Do you want to compile your results in a table? Whatever it is you're used to doing with statistical output, you would do those kinds of things as a Bayesian as well. And in our time together, we will show examples of how to do things like examine the fit of particular models, or compare competing models, or evaluate hypotheses, and how to write and summarize results. Any thoughts or questions before we start diving into particular models and doing Bayes inference on examples? So we're going to start building up to our advanced models, but we're going to start with a core, working with a model based off of a normal distribution or Gaussian distribution, depending on how you refer to it. Here's how I'm going to express it. If we look at the top expression, there is a random variable x, and then that vertical line indicates it is conditional or depends on other things, in particular the parameters mu for mean and sigma squared for variance. And if you picture a normal distribution, you might think about a particular shape or particular curve, and there is an equation that gives that particular shape or curve, and that's what's highlighted there in the second line. There's an equation for the normal distribution. At least in my world of statistical modeling, normal distributions are widely used. They're very commonly employed. And for our purposes in the time we're going to have together, they are foundational in that many advanced modeling and analysis paradigms employ or build off the use of normal distributions. So we're going to review a little bit about normal distributions, because then they're going to play a role for us in regression, and a role for us in factor analysis, and structural equation modeling, and multi-level modeling, and missing data modeling. Let's start with the situation where we have a normal distribution and we don't know the mean. Let's suppose right now we know the variance. Pretend we know the variance. The only thing we don't know is the mean of the distribution. And we have some data X. And this bold X stands for this collection of data. We have data points from some number of cases or participants or records. And so we have this joint distribution of X. If we assume exchangeability, which is a belief that says, for every one person in my data set, I don't think anything really all that differently about them as anybody else before I observe the data. They are all exchangeable to me. You might think of this as related to assuming that they are independent and identically distributed. That's fine. What this implies is that we can build a model that says each of our data points, each of our x's, can be modeled separately given some parameters. And that's what we do with normal distribution models. We say all of our x's, all of our scores are normally distributed with some mean and variance. Okay. So here's our story. We have x's that are normally distributed with some mean and variance. And the situation we're going to treat right now is a situation where there's an unknown mean mu, but we know the variance sigma squared. What we would like is inference about the unknown parameter mu. There is Bayes' theorem for the unknown parameter mu. On the left-hand side in purple That would be what we're after, the posterior distribution for mu, given the known data x and the known variance, because we're pretending we know the variance right now. There are terms on the right-hand side, and as we suggested earlier, we can just work with the numerator, and that's sufficient to get the job done. Let's go through those terms. The term in red is the conditional probability of the data given the parameters mu and sigma squared, which also, once the data are observed, turn into a likelihood function for mu. What is our conditional probability of data? I've said it 3 or 4 times now. Right now, the data are normally distributed with some mean mu and some variance sigma squared. That's our story. For most of us, that doesn't feel distinctly Bayesian, and it's not. You've been specifying distributions for data across probably all of your statistical training. The distinctly Bayesian part for most of us is the term in blue. It's the prior distribution for the unknowns. In this case, we don't know mu, the mean of the data set, so it requires a prior specification. In this context, where the data are treated as being normally distributed, a popular choice for the prior for the unknown mean mu is also a normal distribution. So that prior distribution for mu is a normal distribution which has its own mean and its own variance. And I will just highlight, if I could, PowerPoint hasn't crashed. Oh, there we go. I will highlight my use of this notation. So the term in red is about the distribution of the data, x. The term in blue is a distribution for the unknown parameter mu. What we're saying here is that we're using a normal prior distribution, and that normal prior distribution has a mean and a variance. Have a look at my notation. I'm using in this notation mu sub mu and sigma squared sub mu. Mu and sigma squared I use to stand for mean and variance. The subscript mu indicates this is not a mean and a variance of data, of x. This is a mean and variance of a parameter, mu. These are the parameters not for the distribution of data, but for the prior distribution for the unknown parameter mu. The parameters of a prior distribution are sometimes referred to as hyperparameters. You'll see that term occasionally. A very convenient way to express our Bayesian models is through graphical models. Some of us might be familiar with the kinds of graphical models we're about to discuss. Some of us might not. Some of us might be familiar with other traditions of graphical or diagrammatic models that show up in things like factor analysis and path analysis and structural equation modeling, which can be similar but are not the same as what we're about to discuss. And later on in our time together, when we talk about factor analysis, we'll talk about where the differences lie. Well, what do I mean by graphical models for Bayesian analyses? A graphical model is a visual representation of joint probability distribution. They can be similar, but they are not the same as the things you might learn about as path diagrams in things like path analysis and structural equation modeling. In a graphical model, all entities are represented as nodes in a graph. That could be a circle. As you'll see later, I'm going to use circles and rectangles. Variables will be represented as nodes and parameters. In our graphical models, we will have directed edges or one-headed arrows. Directed, meaning from a source to a destination. And those one-headed arrows indicate a probabilistic dependence among those variables. Something depends on something else. We will have plates, which are really just boxes or rectangles, that will signal replication. We'll show that a little bit. And together, these ingredients form an acyclic directed graph. It's a graph that's directed because it's only one-headed arrows. And it's acyclic in that there is no way of cycling back from where you end back to where you start. There is a particular flow because it's all one-headed arrows. So there's a flow to it, but you can't revert back to where you came from before. Let's build a graphical model for our normal distribution model that we've been just starting to develop. Well, the first node in my graph is xi, referring to a score from a particular person or case or record I. And my story is that for each of those cases or participants or records, there's an x, and that is following a normal distribution. So I'm going to do a few things here. I'm going to model x as a rectangle to indicate that it is a known value to me. I have values for x. My story is that x depends on two things: the parameter mu, the mean, and sigma squared, the variance. I'm writing sigma squared in a rectangle like x because right now I'm saying I know the variance sigma squared. That's a known entity for me. I've written mu in a circle to indicate that is an unknown entity. That's the unknown parameter that I'd like inference about. The rectangle down and the arrows here indicate that x depends on mu and sigma squared. The rectangle or box down here, that's our plate, which signals there isn't just one x. There's an x for every value of I going from 1 up to the number of data points we have. This portion of the graph corresponds to that expression on the right-hand side of the slide. There is another expression we have that's part of our model, which is that the unknown parameter mu was given a normal prior distribution with its own mean, mu sub mu, and its own variance, sigma squared sub mu. Okay, so in our graph, that translates into the parameter mu depending on these higher level or hyperparameters, mu sub mu and sigma squared sub mu. I'm writing those in rectangles as well because I will choose numbers for them. Those are known entities for me. A couple of things to point out here. First of all, there's a lot of mu's flying around on this slide. Mu shows up in a few different places. There is mu here, which is the mean of the x's. That's really what I'd like to know about. But because it's unknown, it gets a prior distribution, which itself is a normal distribution with some mean mu of that distribution for mu and some variance sigma squared of that distribution for mu. I like to put in the subscripts little reminders that say, this is the mean of mu. This is the variance of mu. So I remind myself it's not the mean and variance of data. Questions or thoughts about the model setup, in particular the graph and how it conveys things? I hope folks see like this expression in red corresponds to this portion, which I've also used red for the arrows. This expression in blue corresponds to this portion involving the blue arrows. There's a correspondence between the graph and the system of expressions. So let's get our answer. Let's do Bayes inference to get our posterior distribution. Okay, starting up at the top, we'd like our posterior distribution for the unknown parameter mu, given the data x and the variance sigma squared. Following Bayes' theorem, that's proportional to the stuff on the right-hand side, which is what we just talked about. Data are normally distributed, and the prior for the unknown mu is a normal prior. We're not going to do the math, but you can do the math to derive the answer here. The posterior distribution for the unknown parameter mu is a normal distribution. So in purple here, the posterior distribution for the unknown parameter mu is itself a normal distribution. And again, have a look at my subscripts. It's color-coded in purple to signal that it's a posterior, but the subscripts also communicate that. This distribution is a normal distribution which has a mean and variance, but it's not a mean and a variance of data. And it's not the mean and the variance in the prior. It's the mean and the variance of the posterior, the distribution for mu after having observed x. That's what the subscript is supposed to communicate. We can do the math in this case and know the answer exactly as a normal distribution, because in a model where the data are normal with an unknown mean but known variance, and we use a normal prior distribution, the math works out to be a normal posterior, meaning that the normal prior is a conjugate prior. In this context, conjugate means we used a normal prior and we wound up with the same family, a normal distribution. We're going to visualize this in just a minute, but I want to kind of work out what the details of that posterior are, and then we'll look at things and how it plays out. So the magic of Bayes' theorem is that we combine our prior with the data or likelihood, and you can express it based on individual data points or sample means. It's all the same stuff. And that gave us a posterior. That posterior has a mean and a variance. There's the formula for the posterior variance. If you just look at the colors of the fonts, you can see there's something to do with the prior variance and something to do with the variance of the data and the sample size of your data. And there's a whole lot of fractions flying around. The posterior mean involves, well, let's see, that's the mean of the prior distribution. That's sample size and mean of the data. And this is prior variance and variance of the data. And hey, this term is the same as this term. So there are formulas that allow us to exactly work out the answer. Let's do this. Let's do an example of this and see. Suppose we have a test scored from 0 to 100 that I'm administering to my students. And I'm interested in the distribution of test scores. I collect data from some number of students, and I have the score on the test for every particular student. So I'm going to model the distribution of test scores using a normal distribution. And I'm going to pretend right now I know the variance of test scores is 25. I don't know the mean. That's what I'd like to have an inference about. I administer my test to 10 students, and here are their 10 scores. 91, 85, 72, and so on. Yeah, 1, 2, 3. These are 10 scores. And I've gone ahead, calculated the mean of these 10 scores, and the sample data is 84.1. To specify or conduct a Bayesian analysis, I need a prior distribution for my unknown parameter. In this case, a normal prior distribution for the unknown parameter mu. And I am going to adopt a normal prior that has a mean of 75 and variance of 50. Here's what that looks like. Here is a normal distribution with mean of 75 and variance of 50. This is my distribution reflecting my beliefs about the unknown parameter mu. Mu is the average test score, is the mean of the test scores. So what am I communicating by using this prior distribution? Well, my best guess is that the average test score is going to be in the neighborhood of 75. This is my best guess, somewhere in the neighborhood around here. And I'm pretty sure it's going to be, I don't know, somewhere between the high 50s or low 60s up to the low 90s, creeping up to the upper 90s. These are my beliefs about the average test score before I've collected the data. If I had different beliefs, like if I thought, there's no way people are going to do this well on the test, I'm going to see scores averaging in the 30s, this would not be my prior distribution. I would use a different distribution than this one. But these were my prior beliefs about what the average test score would be like before I ever saw any of the data. So this reflects my prior thinking about the situation. Here it is as the graph. On the left-hand side is sort of the graph generically that we set up a little bit. And then on the right-hand side, I'm filling in, that is, I'm populating the numbers that I've chosen. I know that the variance of the test scores is 25, so I filled that in. And I'm choosing the mean and variance of the prior distribution to be 75 and 50. So I'm just writing them in here. This is me saying, these are the numbers I know. And of course, I didn't write all 10 test scores out here, but we have the data from 10 people taking the test. So let's do Bayes inference. Posterior distribution, let's see, we've got a normal distribution for data and a normal prior for the unknown mean. Just filling in the formulas, our posterior distribution is a normal distribution with some mean and variance. Here's the formula for the variance. It says 1 divided by, let's see, 1 divided by the prior variance, that's 1 divided by 50, plus sample size divided by the variance of the data, that's 10 divided by 25. Rounding to 2 decimal places, that's 2.38. Posterior mean says, give me the prior mean of 75, prior variance of 50. Sample size is 10. Mean in the scores observed in the data set was 84.1. Variance of the test scores we said we knew was 25. And then, oh yeah, this term right here is the same as it was down there. Punch it into the calculator, round to a couple of decimal places, we get 83.67. Here it is visually. This plot has 3 panels. The panel at the top in blue is the prior distribution. This is what I thought about the unknown parameter mu before I observed any data. It's a normal distribution with mean 75 and variance 50. Here is the likelihood function induced by observing the 10 data points. The data are saying the parameter is, what was the sample mean? 84.1. That's also the maximum likelihood estimate. The posterior distribution is literally a combination, a synthesis of these 2 sources of information. It's a product of the, if you like, the height of the curve in blue times the height of the curve in red gives us the height of the curve in purple, the posterior distribution. And that is a normal distribution with mean of 83.67 and variance 2.38. As a Bayesian, that's my answer, the posterior distribution. Nevertheless, we often have a desire to summarize or distill down the information in the posterior distribution for a variety of reasons. Most people we work with don't speak probabilistically. If I go to most of my colleagues and say, I did the analysis, and my answer is a normal distribution with mean 83.67 and variance 2.38, they're not going to know what that means. They're not going to be very happy with me. So we often want to summarize distributions, or we often want to make results from Bayesian analysis similar or analogous to what people are used to getting from things like frequentist modeling and estimation. Okay, well, I know how to summarize distributions. I've been doing that since Stats 101. Let's see, if I have a normal distribution with a particular mean and variance, I can summarize that by giving you the mean. The posterior mean is a measure of central tendency. Because the distribution is normal, it's also the median and mode. So 83.67 is my summary measure of central tendency. I can give you a measure of variability. You could use a variance like 2.38, or most people prefer standard deviations to summarize distribution. So, well, the standard deviation is the square root of variance. So variance is 2.38, so the posterior standard deviation is 1.54. It's just a square root. I could give you a 95% interval. That is, what is the interval within which 95% of the highest posterior density falls? Where is the highest 95% density? It's a 95% interval from about here, 80.64, to about 86.69. And this starts to take on the feel of summaries that people know, like give me a single measure of central tendency, give me a measure of variability, or give me an interval, a range of values. This is often analogous to what we get in frequentist inference, like an estimate, a standard error, and a confidence interval. Here's how I could write this up. I conducted a Bayesian analysis specifying the data as normally distributed. And there I'll write that out. My data are normally distributed with the following prior specifications reflecting my prior beliefs, that the unknown mean had a normal prior distribution. Their answer, the resulting marginal or really posterior distribution for mu is a normal distribution with posterior mean 83.67, posterior standard deviation 1.54, and 95% interval 80.64 to 86.69. Thoughts or questions about this example or some of the ideas we've introduced using this example? Feels okay? Oh, I see a hand. Yeah, go ahead.
Is there a summary measure in Bayesian analysis that looks at how bad the initial priors were?
It depends what we mean by bad. In one sense, let me go back to the picture. This prior, you might think of it as bad in the sense that it doesn't perfectly match what's in the data. I would look at this and say, no, this prior isn't bad at all because it reflects my prior beliefs, whatever they were. The idea that a prior can be good or bad is a kind of debatable issue. There are measures that try to capture how much influence is the prior having, or there are measures that try to capture how much conflict does there seem to be between the prior and the data. So if that's what you mean by bad, I don't want to use the value term bad, because when there's disagreement or conflict between prior and data, it's not always clear that the data should be preferred.
Okay.
Yeah,
So
there are techniques that try to capture the relative influence of each of these sources and how much they're in concert or how much they disagree.
right. I was just mentally comparing the graphical model that is presented here with, let's say, similar squares and circles for structural equation modeling, when you do that, and there's an error term associated with all the parameters. And obviously here there's no error term. So, typically that captures the degree to which the purported model that is being proposed deviates from the data. So there's always the data is being used as a standard for comparison. Here it seems to me that even if the priors are not close to what the posteriors are, that's not a bad thing.
Yeah. And the posterior, this is a nice observation. The posterior here is closer to the data. If you just look visually at the picture, the curve in purple looks a lot more similar to the curve in red than the curve in blue. That's because there's much more information coming from the data than the prior. The data are more informative than the prior in this situation, so that drives the posterior. We could employ there is an error term in the sense of there is variability in our observed measure. So the kind of analogy you're thinking about in path diagrams and structural equation modeling, there are error variability on our variables. We could have written this as a structural equation model path diagram where there would be a variance of the data. Right now, we're saying we know what that variance is. We say it's 25. We're pretending we know that. We're going to build up next towards regression and then later path diagrams for factor and structural equation models where we will see the same kinds of ingredients that you're used to seeing in structural equation modeling show up. And we'll do things like look at model data fit in those contexts too. Great thoughts.
Thank you. I think that.
Okay. So the purpose of this example has just been to kind of refresh what we might have previously been exposed to in terms of Bayesian analysis and its principles. What we're going to turn to in a moment is doing regression analyses. We're going to use some of the same ingredients. We're going to introduce some new terms and some new things along the way as well. So let's expand away from normal distribution modeling to multiple regression. Again, there's a few different ways that we could frame this. Here's one way to think about multiple regression model, that there are multiple x's as predictors and a value of y an outcome for each of n subjects or participants. So for y, we have a collection of y's, an outcome for every person or case or subject. And then x's, well, there's a set of x's from every case or subject, and there could be multiple x's for each person, that is, multiple predictors. There's a few different ways that we can express a regression model. If you're like me, you learned it like this. On the left-hand side, the value of y for a particular case is equal to intercept plus slope times predictor plus slope times predictor plus slope times predictor plus an error term. Errors being independent, normally distributed with mean 0 and some variance. We could also write that as a distribution. That is, this is an equation-oriented lens. An equivalent representation is as a distribution, which is that the outcome y, conditional on the predictors x, and all the regression parameters, intercepts, slopes, and error variance, is a normal distribution with mean given by intercept plus slope times predictor plus slope times predictor, and so on for as many predictors as we have, and then variance given by error variance. You might have learned to write it more compactly with things like vector or matrix operations, which just combines things. There are other ways to combine them too. As a Bayesian, what we're after is the posterior distribution for the unknowns. What are the unknowns in a regression model? The intercept, beta 0. All the slopes or coefficients, one for each predictor, and the error variance of the outcome. And we want that conditional on the observed data, the predictors x and the outcome y. Let's go through the terms. What's the term in red? It's the conditional distribution of the outcome variable y given all the parameters and the predictors. If we assume exchangeability, that is, treat everybody the same, and use normal distributions, standard in linear regression, then what we're saying is the story of linear regression, which is the outcome variable y given the intercept, slope, and error variance and all the x's, is modeled as being a normal distribution with mean given by that regression function, intercept plus slope times predictor plus slope times predictor, and so on, and then variance given by error variance. Here is a fragment, that is a portion of the graphical model that just pertains to this situation here where I have two predictors. So you can see all the arrows are flowing into the node for y, the outcome variable. X influences y, or y depends on x, the first predictor, and the second predictor. And what we're making explicit is that there are parameters too. Intercept, slope for the first predictor, slope for the second predictor, and error variance. I've gone through that a little quickly because that's not the distinctly Bayesian part. This is regular old conventional regression, linear regression, assuming errors are normally distributed. The distinctly Bayesian part is prior specifications. We're going to start with the intercept and slopes, and we'll get to the error variance in a moment. What are all of our unknown parameters? An intercept, one slope for every predictor, however many predictors we have, and the error variance. In order to specify the prior for them, I'm going to go and do them independently, go one at a time. Assume prior independence. For an intercept, a common choice is to use a normal prior with some mean and variance for that intercept. For the slopes, what do we tend to do? Well, we've got as many slopes as we have predictors, and we're going to use a normal distribution for each one of those slopes. So the first slope can have a normal distribution with its own mean and variance. The second slope has a normal with its own mean and variance, and so on up to however many slopes we have. If we treat the slopes as exchangeable, that is, I really don't think much differently about any one as opposed to any other, we can say let's use the same normal distribution for all of them. They don't all need to have their own mean and variance. We can just use the same ones because they're exchangeable. here's a little fragment of the graph for this portion of the model. There is the intercept, and it gets a prior distribution with some mean and variance, so I've written them in the graph. If I have two predictors, I'm going to have a slope for each predictor, and treating them as exchangeable, they're going to have a normal with a mean and variance, and I'm going to use the same mean and the same variance for each. Pretty common in linear regression to use normal priors for intercepts and normal priors for slopes. For variance terms, like the error variance in regression, well, that's where we see more alternatives that people might employ.